about bonding, and last time we got into really the steps to draw Lewis structures for covalent bonding. So remember that when you're drawing Lewis structures, few steps to follow. You want to definitely calculate the total number of valence electrons. And also remember that if you do have a charge, you do need to adjust it. So if it's positively charged, you do need to subtract it off from your total, whatever that positive charge is. If it's a negative charge, you need to add it to your total. Remember that once you have that, that's really important because that is the number you really got to get to in your picture. You do want a logical arrangement. Remember, it's always the least electronegative atom in the middle. And obviously, as we talked about, no hydrogen or fluorine in the middle. We then want to connect one single bond from the center to the outside atoms. And again, that's going to use up obviously a certain number of electrons when you do that, 2 per line. Any leftover electrons go on the outside atom first in pairs until it has met basically the octet rule. And if you still have electrons left over after you fill up all the outside ones, then you want to go to the center. So after the outside, then the center. So we're kind of working outside in. At that point, you hopefully should have distributed all your electrons by the time you get to the center. You want to make sure everybody has met the octet rule. And if they have not met the octet rule, then you could try to fix it. And you can fix that by first trying to do your double bonds. And remember that when we make a double bond, we are bringing electrons in to do that. We're not just adding electrons. We're not just adding bonds. Otherwise, we will have obviously too many electrons in our picture. And you want to kind of exhaust all of your double bonds first. Then if your double bonds don't fix the situation, you want to go then to a triple bond. And you're going to do really the same thing. We're going to bring in some electrons to make that triple bond. At that point, the triple bond should fix your picture. Otherwise, you probably drew something wrong. But he should pretty much have a fixed picture at that point. So remember, we want to think about electrons here in this situation as not necessarily belonging to any particular atom, but we kind of want to as evenly distribute them to all the atoms within that sort of compound. Any questions on that there? Let's just do a couple more here just to remind ourselves. Why don't you draw SO2? Why don't you draw nitric acid as well? And in this case, one of the hydrogens attached to one of the oxygens. So kind of the arrangement is something like this. All right, so okay, so let's take a look. We'll start the first one here, a little sulfur. That is group 6 on the periodic table, I believe. And there's 2 oxygens, also group 6. That's 18 valence electrons. Again, sulfur and oxygen are actually in the same group there, with oxygen being further up, which means it's more electronegative. And there's only 1 sulfur, so he's going to go in the middle there. We're going to do a single bond from the sulfur to each oxygen. That is 2 4 electrons. Got like 14 more to go. We're going to go on the outside. 2 4 6 8 10 12. I still have 2 more to go, and those 2 do go on the center. That is how they get there, by the way. And we should have some dots there on the center atom. At this point, we do want to make sure that everybody is good in terms of the octet rule, and hopefully you can see our sulfur is a little short there. It's got 6, so it is not good. So again, we do need to make a double bond here to try to fix it. In this case, both of the oxygens are equivalent to each other. They're both the same. So I'm going to choose oxygen on the left here, and I'm going to come in and make my double bond by bringing those electrons in. And when I do so, I will end up with a picture that looks like this. This guy will then be double bonded over there. And we will now have, again, still 18 electrons, and everybody now will have 8 electrons. We also could have double bonded on this side, and that again gives us what is referred to as a resonance structure, which essentially is just kind of moving those double bond electrons around. That again is because those double bond electrons are what are referred to as being delocalized. They're just kind of moving from kind of one oxygen to the next, if you will, and kind of move in between. And again, one structure doesn't perfectly describe what's going on here, so sort of a combination of both of these. And usually with resonance structures, we use this little two-headed arrow in between the two structures. So that is sulfate. Sulfate is not double bonded on both sides. It needs those lone pairs, and it should have those lone pairs there. So again, you don't want to double bond or triple bond out of the box. Any questions on that one there? Coming here, a little nitric acid. That's 1 for hydrogen, 5 for nitrogen, 3 times 6 for oxygen, 18, 19, 24. Obviously, this is the arrangement here. Even though there's multiple atoms, there's actually multiple center atoms here. We still do the same thing. We're just going to connect everybody with a single bond, and that uses up 2, 4, 6, 8 electrons. That leaves me something, 16 to go. We're still going to work outside in. So clearly, right, we don't want to put anything on the hydrogen as it is filled, right? So we'll come over here, 2, 4, 6, 8, 10, 12. At this point now, we still have some electrons to put on there. Next outside atom would be the oxygen right about there. So we'll put them on again as pairs as well. And we should now have 24 electrons on this thing. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Is everybody good in this situation? No, our nitrogen here is actually short. It only has 6 electrons. So once again, we do need to make a double bond. And in this particular case, your best double bond options are probably these two here. You could either double bond the top or the bottom. You usually would probably not want to double bond this one, although potentially you could. This bond right here, by the way, is what makes it a acid. That is the hydrogen that comes off. That makes it an acid. And that's a polar bond there between the oxygen and the hydrogen. So we can take a pair of electrons here and bring it in. And that will not put that there. No, like it's written. No, we don't want to draw that. Let's try that again. So we'll double bond that first and then put the oxygen up there. That looks a little better. And we will have this guy like so and over here. And we also could draw a resonance structure for this as well. Again, double bonding over there to the left, single bonding our top guy still. And we would end up with something like this where we double bonded there to the left. Any questions on that there? Yeah. Yeah, you want to, there's some reasons why. One of the reasons is that OH bond is really what makes it acid. That's how the hydrogen is able to come off because it is attached to that. There are some things that will help you, for example, we'll talk about pretty shortly here, that will help you decide, for example, something like that, like, hey, do I want to kind of connect them all together? Is what's known as formal charge, which we'll talk about, and it can kind of help you decide, is this kind of a good structure or a better structure, stuff like that. But typically, if it's an acid and it has oxygen, it will have this bond. The O and the H will always be together. If it is a oxyacid, which is known as, it has oxygen. Yeah. Yeah. You technically could have where the OH is. Yeah. You technically could have. You technically could have probably brought that in and done that. It would have. It's probably not going to be the best because of a formal charge, actually, because it'll make a formal charge of. You'll probably end up with like a positive formal charge over there on the oxygen, which is probably not the best. But technically speaking, you could have also brought the electrons in from that, from those, the oxygen on the right there, where the OH is. Other question. Because technically what would happen, technically, if you brought those oxygen, those electrons in, is technically these electrons would come in, and then these electrons would then get pushed back up to the top, and it actually would then single bond this guy, and you would have a lot more formal charge happening. So it probably wouldn't be the best structure, but technically speaking, it could happen that way. Other question. All right, so again, you need to obviously be able to draw Lewis structures for covalent compounds. As I mentioned before, this does have 2 central atoms. which is kind of important for geometry that we'll talk about shortly as well. So sometimes there's obviously more than one central atom in a molecule or compound that you draw. So speaking of formal charge is something that we use with bonding. And formal charge is basically the difference between the valence electrons in the isolated atom and sort of the electrons in the Lewis structure, how it's sharing electrons. So to calculate the formal charge, you take the number of valence electrons in the atom, you minus it from the number of non-bonding electrons, so those are your dots, minus 1/2 the number of bonding electrons, or you can alternatively just minus the number of bonds, which is basically the same thing. You can do either one, however you want to do it. And this will give us the actual sort of charge that each of these atoms have in these Lewis structures based on who they're bound to, how they're sharing electrons, and so forth. And the formal charge can really help us decide, as I mentioned a second ago, between different structures as to which one might be a better structure than another based on sort of the distribution of the charges on the atoms. So if we take a look at ozone here and we draw ozone, it looks something like this. And if we were going to calculate the formal charge for each of the oxygens that are present, we'll do our formal charge here for, we'll call this oxygen 1, oxygen 2, and we'll call that oxygen 3. So if we do it for oxygen number 1 there, oxygen has 6 valence electrons. For oxygen number 1, there are 2 and 4 non-bonding electrons, minus 1/2 the number of bonding electrons. Remember, each of these bonds have 2 electrons, so that's going to be 4, and that would give you 6 minus 4, which is 2, minus 1/2 of 4, which is 2, which is 0, would be the formal charge. Now, if you want to count bonds, you would just do this, 6 minus 4 for the non-bonding electrons, minus each individual bond here, which is 2, and you get 0 as well. So if you just want to count the bonds rather than doing half the number of non-bonding electrons, it works the same way as well. Now, if we go over to our oxygen number 2 and we want to calculate the formal charge there on oxygen number 2, again, oxygen has 6 valence electrons. In the case of number 2, it has 2 non-bonding electrons, minus, again, 1/2 our number of bonds, so 1 bond, 2 bond, 3 bonds, and that means there are 6 electrons, and that gives me 6 minus 2, which is 4, minus 1/2, which is 3, and that's going to be a +1 happening there. Again, if you just do bonds, 6 minus 2 minus 3 bonds is +1, which is, might be easier just to do the bonds. Lastly, if we do the formal charge over here on number 3 here, we'll do the formal charge on number 3. Oxygen 3. Again, it has 6 for its valence electrons from the periodic table. It has 2, 4, 6 non-bonding electrons. Minus, in this case, I'll just do the bond. It just has 1 bond coming in there. And that's going to give me 6 minus 6 is 0. And minus 1 is minus 1. When you do calculate the formal charge, you should keep the minuses and pluses when you kind of indicate what they are. So when we look at ozone here, it has a formal charge of 0 on this guy, a +1 on that one, and a -1. In this case, our formal charges add up to the overall charge on ozone, which is neutral. So obviously +1 and -1 is 0. And usually for a good Lewis structure, your formal charges should add up to the overall charge of the atom or ion, or what a molecule or ion, if it is. You usually, as we'll talk about, don't really want really large formal charges, 2s, 3s, and stuff like that. That's usually not a great situation either. Any questions on how to calculate that there? So if we take something like carbonate, which has a -2 charge, why don't you calculate the formal charge? Number of the oxygens here, so I'll call that one 1, 2, and 3. We'll start with oxygen number 1 there. And the formal charge again would be 6 because obviously it's oxygen, has 6 valence electrons. It has 2, 4, 6 non-bonding electrons minus basically 1 bond. So I'll just do the bond, and that's going to give me a -1 in this case. If I go to oxygen number 2, oxygen, our formal charge for the guy up on top there is going to be again 6 minus 2, 4 minus, again, we have a double bond happening here, so 1 and 2 bonds. 6 minus 4 is 2, minus 2 is 0. So we have a -1 hanging out on this guy. We have a 0 formal charge on the oxygen on the top. And oxygen number 3 there is going to end up the same as oxygen number 1. We will end up with 6 minus 6 minus 1 bond, which is right there. And that's going to give me -1 in this case. So we got a negative there. Now, if we take a look at some of the drawings here, take a look at our carbon in this case. Our carbon is 4 valence electrons minus 0 for our carbon. And there's really 4 bonds, 1, 2, 3, and 4 bonds, which gives us a 0 in this case. So when we say carbonate is -2, it's hanging out on those oxygens. Each of the single bonded oxygens at that point has basically a -1 charge, which gives carbonate an overall charge -2 based on how it's sharing electrons in this sort of formation. So that is why we have something like nonmetals sharing electrons that overall have a charge because of basically the electronegativity and how they are sharing those electrons. Any questions on that there? Okay. So what can we use formal charge for? Like I said before, we really can use it a lot of times to help us decide, for example, how if this molecule or structure is better than another. And that could also help you with some of the questions like earlier, like, could we just attach it to like, the center, everything to the center and stuff like that. And for some reasons, the formal charges, it may not be the best way to sort of do it. So the best thing to have and a good thing is to minimize your formal charges. If you could get something where a structure has really zeros pretty much for everybody, that's sort of your best sort of Lewis structure that you could draw to minimize the formal charges, get everybody down to 0. That's sort of the best situation. As I mentioned before, if you have Lewis structures with large sort of formal charges like 2s and 3s, those are probably not the best sort of structure. Also, if you have Lewis structures where there's just a lot of charges all over the place versus a molecule where there's not very much formal charge happening, that's also not a good situation. If you're choosing between similar distributions of formal charges, the one where the negative formal charge ends up on the more electronegative atom is more likely a better structure than one where perhaps the negative charge ends up on the least electronegative atom. So, if you end up with some type of structure where maybe you got carbon and oxygen sort of happening, and for some reason your carbon is, has the more negative formal charge versus the oxygen that has the more positive formal charge. When we look on the periodic table, oxygen is more electronegative, is further to the right. So that would probably not be the best structure for that thing, as we would probably want the oxygen to have the more negative sort of formal charge on it. So that sometimes happens as you do these. You sometimes end up with a structure where you got some charges happening and kind of the negatives on the more positive electronegative guy versus the more negative one. So let's take a look at something like formaldehyde, and these are two possible arrangements of formaldehyde. One where we're just kind of attaching everybody to the center, and then we have carbon in the center. And if we draw our two Lewis structures based on that different connectivity, kind of like a straight line versus, this sort of connection with the carbon in the center and everybody connected to the carbon, we get these two Lewis structures. So first off, why don't you calculate the formal charges on each structure, and then use it to decide which one should be the better structure. So use your formal charges to decide between these two, which one should be better. Okay, so let's take a look. We'll start with this structure here. I'll just number each of the atoms, 1, 2, 3, and 4. All right, we'll start with number 1 there, which is our hydrogen. And obviously hydrogen has 1 valence electron minus 0 because there's no dots obviously ever around it. And it has 1 bond coming in, so -1 is 0. So that is 0. By the way, number 4 will come out the same, so I'll just do that one as well. 1 minus 0 minus 1 equals 0 for each of those. Now, if we come to number 2, which is our carbon in this case, carbon is 4 minus the non-bonding electrons, which is 2, minus the number of bonds, which is 1, 2, and 3. And that's going to give us a -1 here. So this carbon has a -1 formal charge. If we now go to number 3 there, which is our oxygen, we got 6 for the oxygen minus 2 non-bonding electrons minus also 3 bonds, 1, 2, and 3. That's going to give us a +1 in this case. So on this arrangement, we have 0, -1, +1, and 0. Any questions on any of those calculations there? And if we look at our other structure, and I'll just number them same, kind of 1, 2, 3, and 4. So number 1 here, which also is the hydrogen, is going to be 1 minus 0 minus 1 bond, which would be 0, as it just has that bond. Number 2 is going to be the same, as it has just that 1 bond, 1 minus 0 minus 1. So we got zeros on those. We come now to number 3, which is our carbon. 4 minus 0, as there's no dots on the carbon, but the carbon does have 1, 2, 3, 4 bonds like it should, is 0. So we got 0 there. And lastly, here we have our double bonded oxygen, which is 6 minus 2 and 4, minus the 2 bonds that are there, which is 0. So the guy on the right there has got 0 for everybody. So if you had to choose between the two structures based on formal charge, which one should be better? It should be the one on the right, as it definitely has minimized the formal charges. In fact, it's zeroed out everybody, which is like the ideal situation. You get everybody to that sort of 0 formal charge. This one, not so bad. It has +1s and -1s and mostly zeros, but we have the situation I was just talking about a second ago. We have a 1 distribution and a 1 distribution, but between the carbon and oxygen, our carbon is hanging out with the more negative formal charge, where our more electronegative atom, which is oxygen, actually has the more positive one. That's also not the greatest situation in that situation. So like I said before, you could definitely use formal charge if you're not sure between structures as to, maybe which one is better, good, not so good type structure. Any questions on that there? Let's try one more here. We did no, I think you have one, right? What do you have on that? CO2, I think. If I'm not mistaken. Let's take a look at one more here. I feel like you have one. Yeah, so I think we did carbon dioxide the other day, and we drew it like so. Now, sometimes people ask, why can you not just maybe triple bond it up, right? And instead of just playing with the double bond, so end up with something like this. So once you do that, calculate formal charges of each of these and decide which one is better. Look here, we'll start on the right, why not? We'll go 1, 2, and 3. All right, so for number 1 here, that's oxygen. We're gonna go 6 minus, obviously in this case, we got 6 minus a single bond there. So that's gonna give us a -1 over here on that oxygen. Number 2, which is our carbon, we got 4 minus no non-bonding electrons, and we do have 4 bonds. Count them there, 3 and 4 happening there. That's going to give us 0, so that ain't bad. And lastly, a triple bonded oxygen, because it looks more chemistry-like with the triple bonded oxygen on there. And we'll do 6 minus 2 here. And it's got a triple bond there, so 1, 2, and 3 bonds. And that's going to get us a +1 in this case. Now coming over here to our double bonded that we got as we followed our sort of method earlier when we drew it. We got our oxygen that's double bonded on the left. It's going to give us 6 minus 4 minus the 2 for the double bond there, which is 0, so that's good. Carbon in the middle there, gonna be 4 minus 0 minus, again, 4. That has 4 bonds. That is 0. And lastly, our third oxygen there, which is gonna be exactly the same as our first. 6 minus 4 minus 2 bonds there. And that's gonna be 0 in this case. Any questions on the calculation? Based on formal charge, which one's the best one? It is the double bonded one like we drew it. Yeah, so that actually is. So that was earlier sort of an answer to the question of can we just like triple bond and double bond out of the box? A lot of times it will not give you maybe the best structure based on sort of formal charge. Any questions on how to use formal charge to help you decide? Do you have to always use formal charge to help you decide when you're asked to draw a Lewis structure? No, you only need to use it if the question does ask you to draw the best Lewis structure based on formal charge. If not, technically you should follow our rules and lay up what we talked about. You know, you should end up with the picture on the left there. All right, so next thing we're gonna talk about is clearly what I just scribbled all over this page here. Let's get rid of that there, try that there. All right, so we talked about resonance, but before we get into that again, we're gonna talk a little bit about bond length. And this is a table of bond lengths and picometers. You don't have to memorize it or anything like that. But if we look at this table, that's the carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. It goes from 154 for the single, 133 for the double, and a 120 for the triple bond. If we look at carbon-nitrogen, single, double, and triple, the carbon-nitrogen bond goes from 143 to 138 to 116. So what we see here is every time we make a bond, the distance between everybody gets shorter. It brings everybody in. If you think about it, what you're doing when you make like a double bond, right, is bringing those electrons in the middle is going to kind of bring everybody in closer. You make a triple bond, going to bring it closer. So a single bond is longer in general than a double bond, and a double bond is longer than a triple bond. They're not like twice as long or 3 times as long, but that is the general trend. So how does that relate to strength? It's basically opposite. The triple bond is actually the strongest because everybody's really close to each other, right? So it's going to be really hard to break that. Followed by the double bond, and the weakest of all of them is the single bond. I think of it like a pencil, right? You get a brand new pencil right out of the box, right? You could snap that thing with no problem, right? You take a chemistry test or so, you're down to like an eraser and a nubbin of a pencil left, right? Very hard to try to break something that's super small, right? Because everything's just together, and that's sort of how it is in here. So again, a triple bond is not like 3 times as strong as a single bond or anything like that, but the general trend is because everything is much closer to each other in a triple bond, you have a lot more electron density between the two nucleuses, which are positives, can kind of bring them in like a glue. It's a much harder bond to break than, say, a single bond. Any questions on that there? So electronegativity, as we talked about obviously earlier, again, our scale of electronegativity increases as you go up to the right and decreases as you go down. As we talked about bond polarity earlier on, and remember that we do look at bond polarity by looking at the differences in electronegativity. Now, there is bond polarity, and there's also, as we'll talk about in the next chapter, molecular polarity. And molecular polarity deals with the entire molecule as a whole, as to whether or not there's sort of equal sharing of electrons, taking everybody into account. Now, bond polarity and molecular polarity are usually not necessarily the same thing. The only place where bond polarity and molecular polarity are exactly the same is when we're dealing with diatomic molecules. And when we're dealing with diatomic molecules, which means there's really only two atoms and one bond, the bond polarity and the molecular polarity will be the same. And it's because of that, like these guys here, for example, Cl2, in Cl2, there is frankly only, I'll draw it correct, there we go. In Cl2, there is only one bond, this bond right here, and the difference in electronegativity obviously is 0, which means that this will be a nonpolar bond. And because that is the only bond in that entire molecule, the molecule also would have to be nonpolar, which means overall that molecule is going to share electrons equally because frankly there's only one bond and we're sharing them equally in that one bond in the molecule. Now we take something like HCl like we see here, which is also diatomic. It is a polar bond between the H and the Cl. Again, you could draw that dipole arrow pointing towards the more electronegative atom, which is the chlorine in this case. Again, it always points to the more negative side. The back part that makes like a plus sign is the more positive side of that bond. And once again, it does obviously have a polar bond. And because that, again, is the only bond in there, this would be a polar molecule as well. So that is really the only place, for example, where bond polarity is basically the same thing as molecular polarity. And that is when you're dealing with something that has only two atoms and one bond. Whatever that bond is will tell you the molecular polarity of the molecule, whether it'll be a polar molecule or a nonpolar molecule. In the case of this arrow, like I drew there on HCl, this is what is known sometimes as the bond dipole arrow, but because this is a polar molecule, this is sometimes referred to as having a dipole moment. And only polar molecules have a dipole moment. And basically, what it means is whichever way that arrow is pointing in that particular molecule is the more negative side of that molecule. And that's because of overall unequal sharing of electrons. So you have a greater distribution of electrons to where the arrow is pointing to, and less electrons, where it's kind of the back side of it that makes like a positive side. So in the case, obviously, here of HCl, we would expect a lot more electrons hanging out over this side, which would make this side of the molecule more negative, this side more positive as the electrons go away. We do not have dipole moments in nonpolar molecules, nor do we draw dipole arrows because there is no separation of charge. It's sharing equally, so there is no negative side or positive side. It's a neutral sort of situation. Any questions on that there? So as I mentioned before, polar molecules will have dipole moments, and sometimes abbreviated with that little symbol there. It kind of looks like a U, and it can be drawn, in any sort of direction. But again, it basically means that this side of the molecule is more negative, and this side is more positive because of that unequal sharing of electrons. And also, if you really calculated dipole moments and so forth, the size of the arrow also indicates that too. So if you had a really small dipole moment, you would have a very small arrow. If you had a bigger dipole moment, your arrow would be a little bit larger as well. So here you can see our Cl2, 0, our ClF, we have a slight dipole moment and a very big dipole moment. We usually have a very big dipole moment in an ionic bond because there is no sharing electrons. There's definitely a distribution of positive and negative from one side to the next. Although we typically don't talk about dipole moments usually with ionic compounds because, again, there's kind of no sharing of electrons, but there is a positive side, obviously, to an ionic compound and a negative side depending on the ion. All right, I think we did this earlier, so we're not going to do that. All right, the next thing we're going to talk about is actually a little bit about energy, although we don't talk too much about energy in this place here. But we will talk a little bit about bond energy. Bond energy is also sometimes referred to as bond enthalpy. And enthalpy is delta H. That is known as the change in enthalpy. And the change in enthalpy is a value that we commonly use for um, deciding if there is too much heat or energy given off by a reaction. Not if there's too much, but if there's heat or energy given off or absorbed by a reaction. If a delta H value is positive, that means overall that process is endothermic and energy was absorbed. If the delta H is negative, then that is an exothermic process, and that means that energy is released. So when we have a chemical reaction, the only thing that we're doing is making bonds and breaking bonds, and that only involves electrons. So when we calculate the change in enthalpy for a reaction, we basically can add up all the bonds we make or break and add it to all the bonds we make. Yeah, so making and breaking bonds. Now, the process of breaking bonds is endothermic. You have to put energy in to break a bond. So if you have a bond, you put energy into that bond, everybody gets enough energy, they wiggle away from each other, and they break apart. If you need to make a bond, what you have to do is basically release energy. Everybody has a lot of energy, so as you release energy, they slow down, and they can kind of come together to make the bond, and that's an exothermic process, which means, again, more negative versus positive in terms of values here. So we'll take a look at one here as to sort of a table. So this is a table of bond energies or bond enthalpies, and it is different, obviously, for single bonds versus double bonds versus triple bonds. And you do want to make sure that you understand, what type of bonds that you are looking at. So if you're going to calculate this change in energy based off of the reaction of breaking and making bonds, you might want to quickly sketch a Lewis structure if you're not sure what it looks like, because you want to make sure that you're counting if it is a double bond versus a single bond. As we just talked about, obviously there's a different amount of energy required to break a single bond versus a double bond or a triple bond in this case. So if we take a look at this and we draw it up here, this is sort of what it looks like very badly, so I'll redraw it here. So we have our methane here. We have our chlorine. It's going to go here to this. And we got one of those as well. All right. So these are just kind of quick Lewis structures. Obviously, I didn't put the non-bonding electrons in there or anything like that because it's not really so important, in this case. So really what you want to do is just sort of count up everything almost like an accountant here. So I know I got to pretty much break everything on this side, and I got to make everything on this side in terms of the bonds. So I'm just going to start with the carbon-hydrogen single bond. I got to break 1, 2, 3, and 4. I have to break 4 of those bonds. I could go to my table and find the carbon-hydrogen single bond, which is right there, and it is 414 for each of them that I break. So that's 414 kilojoules of energy to do that. I also am going to be breaking over here a chlorine-chlorine single bond right there. So I got to break a chlorine-chlorine single bond, and that is one of those. Again, I'll go to my table here and find the double chlorine, which is right there at 243. And that's going to be 243 kilojoules. That is all the energy that I need to break everything that's on the reactant side. So if I do that, that's going to be 4 times 414 plus 243. So that's a grand total of 1,899 kilojoules of energy that's going to be required to break every single bond that we have going on the reactant side. It is endothermic, as I talked about before. We got to put that energy in. So it's actually a positive 1,899 kilojoules of energy needed to break those bonds. Now we need to basically add up everything we are making on the right-hand side. So over here for our making, we have 1 carbon hydrogen, 2 carbon hydrogens, 3 carbon hydrogen bonds. So for carbon hydrogen on the making side, we have 3 times 4, 14 kilojoules. Now, we also have I'll go here. We have a carbon chlorine bond right there that we need to break. So that's a carbon chlorine bond. We have just one of those. So again, we'll go back to our table and find that somewhere right there at the bottom, 339 it looks like. So we'll go 339. And lastly here, we're going to make one last bond, which is our hydrogen chlorine bond right there. And that's one of them at, not that, go back here. It was hydrogen chlorine. So hydrogen chlorine right about there, 431 it looks like, at 431. Yeah. So if we do that in terms of making, we'll go 3 times 414 plus 339 plus 431. That's going to give us 2012 kilojoules of energy to make it. Now remember, making is exothermic, which means technically speaking, every one of these numbers are negative because it's exothermic, and that would give us a negative 2012 amount of energy that has to be released to allow those bonds to come together. So now that I know how much energy was required to break all those bonds, and I know how much energy was required to make all those bonds, what is left is basically to calculate our delta H of this reaction. And we basically just going to add those numbers together. The amount of energy required to break, and on the reactant side, added to our amount of energy required to make on our product side. And that's going to give us a net, in this case, of negative 113 kilojoules of energy. So overall, this reaction based on bond energy, making and breaking all those bonds, is it endothermic or exothermic? This reaction is, it is exothermic because we have a negative here. So this would be exothermic here for our delta H. So you can calculate the energy based on bond energy here by, again, just kind of adding up everything. Like I said, you just got to be careful of, do you have double bonds, single bonds, or triple bonds? So if you're not sure what it looks like, you might want to sketch a quick drawing of a Lewis structure so you make sure you have it. Also, sometimes sketching the Lewis structure is really good so you don't miss a bond. It's sometimes very common. People, for example, if there's 2 carbons attached to each other, people oftentimes miss that inner bond between those two by not doing that. All right, so why don't you try one here? Why don't you try this one here? H2 plus O2 makes H2O2. Again, make everything on this side. So we definitely have a hydrogen single bond we're going to break, and that looks like it is 436 there on the chart. We are also going to break here a oxygen double bond. And on the chart there, where are we at there? Right there, 498 looks like. So 498 kilojoules. And I think that's all the breaking we got going on there. So we're just going to kind of add them up there. And we will end up with 436 plus 498. It's going to be a 934 kilojoules. Again, remember, breaking is endothermic, which means it's going to be a positive number here. Now on our making side here, we are going to make oxygen-hydrogen single bond, one on each side. So we got 2 of the oxygen-hydrogen bonds there. And we can go 2 times our oxygen-hydrogen, which is right there, 464, it looks like. 464. And again, why it might be beneficial to draw some of these, a very common something like this, people will oftentimes miss that kind of center bond between the two guys. And that is one of the oxygen-oxygen single bonds in this case. And that is somewhere on here, right? I feel like it's right in front of me. Where is it at? There, right there, right above the other one there. That would be good. 142 looks good. All right, so we got a 142. Again, this break-in is an exothermic, so technically these are all negative numbers here. So we can go 2 times 464 plus a 142, going to give us a negative 1070 kilojoules. So our delta H for this reaction is, again, just going to add those together. We can go our breaking 934 plus our making a minus 1070 kilojoules. So 934 plus our 1070, that's negative 136 kilojoules in this case. And again, it would be exothermic, as we did end up with a negative value for delta H. Any questions on that there? Also, don't forget, for example, if you have coefficients in the balance equation, you do have to take those into account. So, let's just say you had an equation where it said 202. That would mean you wouldn't have just one of those, but you would have two of them, right? And you would have to break both of those bonds, or if it was on the product side, make both of those bonds. So if you do have coefficients in the balance equation, that obviously adds to the number of bonds that you're going to make or break. So you got to take that into account, because obviously you'll have more than just one of those molecules. Any questions on that there? Yeah. All right. So we talked about resonance structure, and really resonance structure is anytime you have these electrons which are delocalized, or basically can move around from one spot to the next, and you could draw an equivalent sort of Lewis structure for that molecule, like we saw with carbonate, for example. And that's because not one sort of structure by itself truly sort of describes what's going on with it. And usually in between resonance structures, we do draw these little arrows heading in both directions. So that carbonate, or that even ozone is an example of that. We could double bond here, but we could just as easily double bond over here to the right. And we would obviously have our double bond over there and our single over here, making it our resonance structure. With our carbonate, which we did as well, again, we could have 3 resonance structures. And as I mentioned before, essentially those double bond electrons being delocalized basically at any given point in time can kind of be moving between the different oxygen atoms. And again, the true structure may be somewhere between all those type of things. Once again, as we talked about, if you are asked to just draw a Lewis structure for carbonate, you could draw any one of them. And then obviously if you had to draw all the resonance structures, basically just kind of keep moving the double bond around to all the possible sort of places that you could put it. A benzene ring is something you'll see a lot in organic chemistry. It looks something like this. It's a 3-carbon ring with 3 double bonds in it. Each of these are carbons. And each of these carbons have hydrogens, 1 hydrogen off of it, although we never use it in line structure like this, draw any of that, but it's usually sometimes represented just like so. You could draw a resonance structure where basically those double bonds just kind of move around the ring, and you'll end up with a benzene that looks something like that, where they basically just shifted sides. And sometimes you'll even see people draw benzene with like a little circle in the middle, and that indicates that those double bond electrons are basically delocalized and they can move around the ring. So you'll sometimes see that drawn. If you take organic, you will draw that all day, every day, and be judged on how you draw your ring. No, I'm just kidding. Walk away, kicked out if you draw bad. All right, we get the idea of resonance structures here, a bunch of different ones you could get. Now, we're going to talk about exceptions to the octet rule. So there are some exceptions to octet rule that do pop up along the way. And some of these exceptions are what we're going to talk about right here. The first one is what's known as an incomplete octet. And an incomplete octet means that it basically has less than 8 electrons around it. And there are certain elements, and I would say probably this 3-pack of beryllium, aluminum, and boron, and probably boron is the one that you'll see the most, are typically the ones that are just fine with 6 electrons. That's again why it's known as an incomplete octet. It's actually electron deficient, and it can act as an actually acid later on. When you go to 200B, you'll learn about it, but it's actually missing some electrons, and it's perfectly fine in that situation. As you can see here, again, our boron has only 6 electrons, and it's okay with that. So those 3 are typically the ones that you see able to do that. And I would say probably most of the time, boron is going to be really the one that's going to come the most, as aluminum and beryllium sometimes are, a lot of times in sort of ionic compounds. Here's beryllium dihydride here. And again, our beryllium here actually only has 4 electrons, as opposed to obviously 8. The next couple of exceptions to the octet rule are the odd electron molecules. So sometimes there are molecules that have an unpaired electron, sometimes referred to as like free radicals because they have an unpaired electron. They're usually very, very reactive because they don't like to have an unpaired electron, so they're trying to fix it, and that usually makes them pretty reactive. A lot of in the atmosphere, chlorine and chlorines can end up like this a lot of times. And again, here, if you look at NO, we will end up with an unpaired electron there in nitrogen, and also NO2 as well will end up with an unpaired electron on the nitrogen. Now, probably the exception to the octet rule that we will deal the most with is the expanded octet. And the expanded octet are elements that can go over 8. So after they told you not to go over 8, you can go over 8. And so there are definitely ones that could go over 8. You could have 10 or 12 electrons around the central, or any atom really, that it can do that. And it usually happens on elements right around on the periodic table. If you look where sulfur is, go a little bit to the right, a little bit to the left, and down. Those guys have the ability to go more than 8 and do the expanded octet. That is because sulfur, as it says there, is on the 3rd period. And on the 3rd period, that is N is equal to 3. And what are the orbitals on the 3rd energy level? There are s orbitals, right? There are p orbitals, and there are d orbitals. That's where they first start to appear, because L could be 0, 1, or 2, S, P, and D, right? So they have that ability to do that. Now, because they have available to them the d orbitals, they actually have a place to stash the extra electrons. So they can use those d orbitals to put the extra electrons in. So again, kind of sulfur to the left, to the right, and down, really in the non-metal region, we're kind of talking. They have really the ability to kind of do that. That also means that can carbon, nitrogen, oxygen, or those guys on period 2, can they do the expanded octet? What do you think? The answer is they cannot do the expanded octet, because that would be N is equal to 2, which means L could be 0 or 1, which is an S and a P orbital only. They do not have d orbitals available to them, so they should never ever go over 8 for sure. Yeah. Yeah. It is, yeah. So that's exactly what it is. And again, um, because it's really unpaired, it doesn't really like to be that way. Um, it tries to fix it, so that's why they're very reactive to try to bond up and kind of complete the octet, if you will. in that case, because it's really short the octet on that side, right? On the nitrogen side, for example, it's got 2, 4, 6, and 7 electrons. So that's why they're very reactive, and they would have only one that loose electrons, and it's trying to make some bond and try to fix it and stuff like that. And again, on the second period, they can never ever go over 8. And that's why when people start drawing things with carbon, they just keep adding bonds and stuff like that. Just when they go to organic, they just keep like drawing lines to carbon a lot of times, and the carbon ends up with like 42 bonds. It's like way too many. There's never ever go over. So the only things it could go over is starting on that third period around sulfur and down can do that. So for example, SF6, S is 6, and there's 6 fluorines, which are each 7. And basically in this situation here, we would have our sulfur, and we would have 6 fluorines around, however you like to arrange it, kind of like this maybe. I got there 1, 2, 3, 4, 5, 6. And basically if we do a bond all the way here and basically fill up the octet around all of the fluorines, it will look something like this. And sulfur is perfectly okay like this. And in this particular situation, sulfur will end up with 2, 4, 6, 8, 10, 12 electrons around it. And it's able to do that, and it's perfectly fine doing that. So we definitely will see the expanded octet a lot in here. There's a bunch of geometries that go with the expanded octet that we'll talk about. And I would say out of those 3, probably the expanded octet is the one you'll see the most, followed by probably the incomplete octet. Probably not too often in this class. You'll come across probably a odd electron, but it is the one of the 3 sort of exceptions. Any questions on that?